Hello and welcome once again for another episode of Profiles in American Funded Research. I'm excited to have my guest today, Jeremy Riousset. He got a bachelor's degree at the École Centrale de Lyon, as well as a master's there. Then he got another master's at Penn State, as well as a PhD. And some stuff happened in between, but now he is an associate professor at Embry-Riddle. Did I get everything correct there?
Yeah, absolutely.
And I, Jeremy, on today to discuss a project entitled Experimental Study of the Role of Secondary Electron Emission in Atmospheric Electricity. So I would like to give you an opportunity to just give like a brief overview of the project and then we can jump in.
Well, the um, short story is atmospheric electricity describes any electrical process that happen in the atmosphere that goes from what we know as lightning, but also a very variety of electrical discharges that are associated with it. On them, there are multiple yet unknown physical processes related to initiation, propagation, and termination. In that particular case, I'm really focusing on the initiation. And this project has two elements. The science and research element is to try to understand the initial stage of the lightning, in a sense, by trying to do it in a controlled environment, which is extremely challenging for something like lightning. And the other element is how we can share what we learn along the way and build a tool to teach the scientific methods we are using to a wider audience using an open source platform.
Thank you very much. So I wanted to start because I doubt probably that many people are familiar with these type of phenomenon. So I was hoping maybe you could touch on this in a bit of detail, which is what are transient luminous events?
Transient luminous events have a very fascinating story behind them. So, of course, we know lightning with non-lightning because it's a visible electrical discharges. We've known their nature since Benjamin Franklin as essentially a flow of electricity. But in the mid 90s, roughly, we discovered that were not the only electrical discharges that were existing in the atmosphere. A whole variety of discharges are also developing in our atmosphere, especially when we have a thunderstorm. The TLEs describe essentially transient luminous event, as their name states, something that is visible but is very short. And those include what we call typically jets. Jets, you can think of them as the counterpart of the lightning we see. Most lightning that we see don't ever actually leave the cloud. They just appear to an observer as just a bright illumination of the cloud. That is most of the lightning we see. A lot of, frequently you can see the part of the lightning that escapes the cloud. We call it a cloud to ground. Basically, that's what hits a lightning rod. But going to the ground is not the only path for lightning. You can have another path that goes up, and that part going up is called a jet. We have typically 2 or 3 categories, depending on who you ask, depending on essentially how high they can go above the ground. The most spectacular one is called a gigantic jet, which you would observe as a channel that goes from the top of the cloud up to the atmosphere, so the ionosphere, roughly 90-kilometer altitude, so give or take 60 miles. That's the jet. That's the second element. The third element we call is sprite. A sprite, unlike a jet, does not originate inside the cloud. It is occurring as a consequence of a lightning, and it will occur starting at roughly 80-90 kilometers and go down and up a little bit. And it's a very massive but very brief electrical discharge. Massive meaning it's roughly look like kind of a jellyfish, and it goes down about 40 miles, and it's about, I'd say about the same in terms of width, 40-50 miles. But it's not as intense, more diffuse than a lightning. And there are a few others that we're going to call like a halo, that is like a ring of luminous ring that goes, that the ELF is a luminous ring that can develop above the cloud, and halo is another event. There are a few of these. Those are all what we call transient luminous event, TLEs. And the reason I was calling them interesting is because the way they were discovered, if I believe that was Dr. Westcott and Sandman at, I think, the University of Alaska Fairbanks, first reported that. They came from looking at the black and white cameras that were used to film the shuttle takeoff. And at some point they were looking at them and saw this luminosity in a frame of the camera, observed it, and started documenting it, calling it sprite. And the interesting element to it is that once this has been established, like, hey, look, we see that, we were able to backtrack observation of those more than 50 years before by pilots, airline pilots, to say, yeah, we see them all the time. And of course, for a scientist, like, why don't you report them? What the hell is going on there? Why didn't you report them? And essentially, pilots said, because if I say I see flashes of light while I'm flying, that is a direct and sure way to get my license revoked. So once they were established, we were able to backtrack that. So that's a funny story behind all these luminous events.
Now, how are these related to lightning? So do these transient luminous events, do they happen around the same time as lightning? Do they happen independent of lightning?
Well, we can call them TLEs, so it might be easier and less of a mouthful. It depends on them. Some of them, like jets, are believed to be continuation of lightning. So basically, you start as a regular lightning, but a special configuration of the cloud would allow them to go up. That's the first step. Jets are sprite and other events are typically a consequence of lightning, meaning that lightning will trigger a change in the electrical structure of the cloud, to stay general enough. And this change of the electrical structure create the right conditions for starting this event way above the cloud. They all occur during a thunderstorm. They are related to a thunderstorm, and either they are directly connected to the lightning, or they are related to what the lightning does to the cloud, and then that will trigger the discharge. So as far as I can tell, you cannot have a sprite without having a lightning first, but you can have lightning without having the sprite.
And are these visible from space? So like, are the astronauts able to see them? Yeah.
Yes, actually, we have a lot of data from the space station. We have dedicated instruments. The two that come to mind, very successful, was the visual camera, I think, that was run by Taiwan. And we have a few other satellite missions. And my colleague gonna be mad at me for forgetting the names, but I think LIS is an instrument, and I don't know what the status, but the original European mission called Taranis was also meant to specifically observe those. Unfortunately, blew on site with a launcher a few years ago. I heard a few months ago there might be a replacement for that, but yes, they are observable from space, and they are a very useful way to do it. Challenges being two, when you observe from space, you have the distance, so they are still relatively close to the ground. I mean, I'm talking the ISS is going to be at, let's say, 400 kilometer altitude. These develop between 0 and 100 kilometer altitude. So you're still like 3 times further when you're above the ground, above the cloud than you are when you're on the ground. And the second, and it's the same problem when you're on the ground or when you're in space, a lot of this is enshrouded in the cloud and blinded by the fact that the lightning are typically a lot more energetic than those events. So those are the challenges.
Now, because I think that it seems to be related to your project now, coming back
Mm-hmm.
into the details a little more. Can you explain what Townsend discharges are?
So a Townsend discharge is what I would consider as the fundamental aspect, the fundamental element to it. So the reason you have an electrical discharge is essentially creating something that was not able, a path. So you take a material, typically in our case can be air, but if you're on another planet, can be carbon dioxide, can be pure nitrogen. On Earth, it can even be like in a battery, but the fundamental idea is you take something that is not able to conduct current and you make it conduct current. So that's the gist of an electrical discharge. Discharge just meaning not conducting, becoming somehow conducting. Townsend discharge is how you will create that, starting with the creation of this path. To create this path, you need to put constraint, and those constraints are related to the number of volts per unit length. So that's called the electric field. So how many volts are you going to be able to put on a certain distance to force electrons that were not really able to transport electricity into making them transport electricity? That's what we call the breakdown. This ability to say, okay, now I have a path to conduct the electricity. The Townsend discharge is how you create that. So how many volts does it take to turn a previously non-conducting material into a conducting material? That is represented by what we call the avalanche process. Namely, if you think as I'm trying to describe it in the easiest way possible. You take an electron that will hit an atom. When this electron hit the atom, it will be able to not only come out itself with some velocity, but also take an electron away from this atom. So as a result, you will have your original atom minus an electron, that's an ion, the original electron, and the freed electron.
Is that
Take those two
the
electrons.
is that secondary electron emission?
That's typically the primary electron ionization.
Okay, that's
And
the primary. Okay.
when you actually continue that process, this electron that you just have now, two of them, you started with one, you hit an atom, you have two, they hit an atom, you get four, etc. The secondary electron is the ability to, or the likelihood for this newly freed electron to create more and more avalanches. And that becomes the secondary electron emission. And that is what is very poorly characterized and what we understand. Because if we understand that, we understand specifically, we understand really better how these avalanches are able to exist. And if we understand how these avalanches exist, we understand how this breakdown, this very first step of breakdown, of turning something that does not conduct electricity into something that conducts electricity. And that is relevant for laboratory discharges, but also for all electrical event we have. The only change we have is how you apply the voltage. In a lab, you have two electrodes. In a cloud, we have a slightly different process. If you want, I can go into details, but the gist of it is still how many volts you put on a certain distance.
So you have to have depending on the material, a certain level of voltage in order to create the ionization, I think is what you're
Yes,
saying.
exactly.
So you have to have when you hit this minimum value, depending on a particular type of gas or whatever. So I'm assuming that that value changes as you change the gas, right? As you change what
Exactly.
gas is in there. But
And not just.
that is what allows you to then ionize the gas, which makes the
Mhm.
gas charged, which then makes it conduct electricity now.
Exactly. And to continue on this, on what you're saying, you're right. Obviously, it depends on the nature of the gas, but also that original electron doesn't come out of the blue, and it has to come from either the gas is one option, obviously, but it can also come from what we call the electrodes. So if you have your voltage, you can free it from the plate. If you think about it as a battery, you basically release it from a pole, one of the electrode, and that means that the electrode itself is a possible source, which means that the ability to create this charge also depends on the material of the electrode, the shape, the condition, etc. And that is critical because that becomes really the heart of the secondary electron emission, which is not a primary that is purely gas dependent, that we are able to kind of characterize relatively well, but also on, okay, I have those, but also the contribution of these seed electrons and where they come from. And that's the main contribution of a secondary electron emission. And I like in the work I proposed, my student came out with a couple of very good quotes that I like, that's been used for um, that stayed for the last 20-30 years now, roughly. When we describe the secondary electron emission depends on the gas, the electrode material, the electrode state, meaning is it really eroded or not, the shape, and other things. So basically, we have like it depends on a lot of things. And I thought, okay, well, let's get maybe a little better than it depends on pretty much everything. And that's the gist of what I'm trying to do here. And I have to give kudos to my former grad student, graduated with his master's last December, for actually pinpointing that discrepancy in the literature. So his name is Jared Nelson, and yeah, he pointed out. I thought it was really good as showing, hey, there is something there that is not clear, and let's dig up. Let's dig up.
Yeah, so I think actually I read in your statement, one of your statements or whatever, that you are actually even trying to look at geometry as well, like how the
Yeah,
geometry affects
exactly.
that. So that's really interesting that all of these different variables you're trying to account for.
And it's really even an older problem, because if you think about the reason we have those discharges, and the most familiar element to it that we know is that, okay, we have lightning and we have a need to protect ourselves, not just on earth, but on any element. Electric cars battery, you have to figure out how much voltage you can put without exploding the battery. That is part of these constraints are directly related to that. There is a few stages, obviously, so, but the gist of it is still an idea of how much volts you put before something that is not conducting becomes conducting. So again, you want to make sure that you build an electric circuit where you're not going to reach that threshold if it's not something you want to. You don't want to create an electrical discharge in your battery with unwillingly. So that's one. But yeah, and that's going back to the geometry. We know how to channel lightning pretty much. So basically, we know how to protect ourselves from lightning since Benjamin Franklin, through a lightning rod. So that was over 200 years ago. And now a couple of fun facts about it. Back in 2000, there were studies in New Mexico of what is the best geometry for a lightning rod. We don't have an answer. we don't have an answer whether we should make it pointy or we should make it a little rounded, or how big it should be, a very big cylinder or should be a tiny cylinder, should we make it a sphere on the top or not. We don't really know. So that's how important the geometry is and how clueless we are. And another interesting fact, if I remember an article, I think it was Physics Today a while back by Phil Kreider, Dr. Phil Kreider, which pointed out, I think, that Ben Franklin believed that the lightning rod would prevent lightning, not channel it, by silently discharging the cloud. So it's working, but for the wrong reasons.
Yeah, that's interesting. I didn't realize that Ben Franklin didn't know that it was just sending the the charge to a ground basically,
Yeah.
and discharging it through the
Yeah.
excess of the ground.
Instead of, he was expecting to repel lightning rather than attract it.
That's really interesting. Um,
And 200 years later, we still don't really know what's the best way. Although I know quite a few companies that would try to sell you advanced protection device. I would not invest money on that. My 2 cents. I would just make my lightning rod taller. That would be my advice.
fair enough. Actually, good advice for our viewers. Now, you mentioned that that the different gases might have a different amount of voltage that they need in order to create the ionization. But um, my question then goes into when you think of air, because that's where we see lightning and stuff. Air is actually not just like a single gas, it's a mixture of gases. So do we know how that mixture plays a role in that voltage, that minimum voltage?
Um, in the primary ionization, yes. In the primary ionization, we do know, and we do know it because we know the exact composition. However, there are again a few, like in everything inside, a few caveats. For example, I was playing with this idea of calculating the these values, and when I calculated these values on different planets, um, you have to account for various characteristics. Obviously, Earth is, I'd say, ballpark 80% nitrogen, 20% oxygen, and you look at Mars, it's going to be 95% carbon dioxide and 5% atomic oxygen, and Venus is going to be like 99% carbon dioxide. So essentially, you will do that. And what's curious is this ultimately goes to the very details of what it's made of. And what's something that surprised me is the minute, the trace element, can have a major impact. So it's not necessarily the big gas have a big effect. Honestly, obviously, that will define the most the bulk of the behavior. Essentially, how many volts per you need to turn the gas from non-conducting to conducting. But depending on the trace element, especially things like atomic oxygen, which is basically take your typical oxygen on Earth and split it in half, those are very reactive molecules. They will want to recombine, and they will have a very strong effect on how the gas behaves. So it's not just knowing what it's made of, but it's also knowing in very high details what is made of. And in our models, even well characterized or well very familiar element like water vapor can be challenging to model, because water is a complex molecule and it has a lot of very particular behavior that we're not yet able to fully characterize. So that could make a difference of several percent, if not tens of percent, in terms of uncertainty on the values that we have.
Now, how does that? Because you mentioned you started off by saying, yeah, for the primary. What is known for the secondary? Is there anything known, or is that really like you're going to be one of the first delving into this? Like how much is known in the secondary emission, electron emission?
We we know a range of values. Typically, there have been experiment in quantifying um, specific gases, specific electrodes, but trying to create a rigorous approach where we're gonna try to decorate the effect, I believe is new, as far as I can tell. Namely, looking at, okay, I'm gonna do the same gas, but I'm just gonna change the geometry. Or I'm gonna keep the same geometry, but change the gas. And looking at how the discharges voltage change. And the second very important element of a study that is sometimes maybe the least obvious, but devil is in the details, is that a lot of this do not necessarily show the uncertainty. On all the studies I've seen and looked at before looking at this work, when we establish, okay, let's say I'm on Earth, I'm gonna need 400 volt for turning air from dielectric, from non-conducting to conducting. If I have a atmospheric, if I have a 760 torr in a small gap, let's say. So we have a value, 400 volt, right? But that is not, to me, as a scientist, is not enough, because I'll say, okay, is it 400 or is it 355 or is it 395? Is it 405? So what is my uncertainty? And what we are trying to do as well is to say, okay, this is a range, but it's also what we don't know. I know this value, but I also know how far off I can deviate. And that is very important, because that goes directly into a safety factor. You go to Mars, you don't want to know the theoretical value, but you want also to know how sure you are about this value. And I'm talking about Mars because even if we don't have currently a definitive answer whether there is lightning or something going on Mars, there is a possibility that our presence can create the condition to create lightning. And so that's something to be mindful, because having lightning damage on Earth is difficult because fixing is a pain, but on Mars, there is no second chance. So
Yes.
that's one of the long-term element that we look at.
I imagine also if we could nail down certain things about lightning here on Earth, that would also help us designing electronics and things in a particular way.
Absolutely, absolutely. The damage to the effect of understanding lightning on Earth has multiple implications. Of course, it has protecting our electronics, but not just that. It's important for industry, but it's also important for farming, surprisingly enough. I live in Florida, and in Florida, well, we have a lot of lightning, and we also have a lot of cattle. And cattle doesn't have the um, scientific logic in a thunderstorm. What do I mean? Well, when it's rainy and there is storm, the actual advice is get inside. For cattle, is that, oh, it's raining, I'm gonna get under a tree. And it's a terrible idea when you have a lot of cows going under a single tree, especially in Florida where it's very flat, because the tree is gonna be your lightning rod. And that means that if lightning strikes, it's not gonna hit a cow, it's gonna kill entire cattle. So that's really also one of the huge implications for understanding this effect.
Believe it or not, I'm actually very well versed in cows because I grew up on a small farm myself. So we had some cows, and yes, they definitely don't have a scientific mind. But 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 in any case, now when you're doing this, obviously you're developing, as I know, some theory, but you also need to map that back to the real world somehow. So you're also doing some experiments. Can you discuss a little bit the experiments and the kind of equipment that you need for doing these experiments?
Yeah. So we do have obviously what you describe as a theoretical modeling element, and we also have a experimental lab. So the experimental lab requires um, an ability. The novelty of our experiment is to have it as automated as possible. To create a discharge, if you put it simply, you need to put voltage between a gap. That means a couple of things: knowing the size of your gap, the pressure of your gap, because if I track back to TLEs that we're talking about, the very big difference between lightning and, let's say, a sprite is the altitude, and the altitude is related to the pressure. So when you look at the pressure, we need to know exactly how much we have. So that means having a tank. Essentially, we have a glass tank. Inside, we have two electrodes for which we can define the geometry. So do we want them to be plates? Do we want them to be a point and a plate? Do we want them to be point and point? Because all those have effect. How big do we want the electrode? And we need to control all these elements very precisely. We need to know exactly how much voltage, how much volts we put on this electrode. So we need a power supply. Ours right now goes from 0 to, we upgraded, so it was going to about 1,000 volt, and a new one, thanks to the project now, is going to 5,000 volt, to be able to put enough voltage to get the gap. We need to also fill the tank or empty the tank, so we need to have pump to remove gas or add gas. We need to know exactly the pressure, so we have a pressure sensor. And to control the inflow and outflow, we have a mass flow controller that is connected to the pressure sensor to know exactly the amount of gas you have in there. And to empty and open the tank, what we have is, what we're mounting now is remote controlled valves. So that allows us to say, okay, when the pressure is at this level, close the valve, rather than doing by hand. You know, it's like, oh, I'll read the pressure sensor, I'm going to close now. Because that allows us to know exactly, okay, if I have a reader on the pressure sensor, it's not all I want. I want the reading, and I also want the uncertainty on this reading. Same way, when I apply voltage, I want to know how much I applied, and when I increase, I want to know by how much I increase every level. All of that is connected to a centralized computer. And the last element, and that might be the trickiest one, is to measure when you have the discharge, because the first thing you do is you increase the voltage until you see the L in TLEs, the luminous element. But the truth is, we're not interested necessarily as a luminosity, we're interested in the transition from not conducting to conducting. And that manifestation is when you have a flow of electron, a current, and for that we have an oscilloscope that will record this appearance of the current. And so again, that allows us to have a now automated signal saying whether or not I see the discharge, it doesn't matter whether it started emitting photon and light. What I have now is, oh, I have a current, so I know that I have a discharge. I'm going to record the pressure I'm at, I'm going to record the voltage I'm at, knowing exactly how much I increased. And this entire automated system allows us to have our entire bench.
And also, as you mentioned, measurements on uncertainty. So that's great. So
Exactly.
another
So that we have an automated feed through. That's also very fun because I got my student to make some videos. The idea is that you want to know exactly how big your gap is, and the easiest way to do it is not to take a ruler and measure, is when you have a motorized feed through, you get it to actually screw down until it touches. When it touches, you close the system. That gives you an electric signal, tells you, okay, that's you touching, and then you count back. And as you screw down, so you see before an experiment, you will see the electrode slowly going down, touch, and then go back to the exact distance we want. with exactly knowing the pitch of the screw of our motor, we know exactly how big the gap is. It's very cool to see, honestly.
Now, you mentioned another part of this project there's an educational element as well. So you have obviously the
Yeah.
experimental, there's a little bit of theory, or maybe a lot of theory, but there's theory, and then the educational part. So could you just explain Pythagora?
Yes. The idea is that an observation I have is when my students come to me, especially undergraduate that have an interest in getting experience in research, the steps to bring them up to speed on what we want to do are the same. You always thought, okay, well, you're gonna need some programming, and I figured like, well, with these students, rather than just asking the same thing, I'm gonna ask him to document them. What are the hurdles he is encountering? Because I don't want to teach for the sake of teaching programming. I'm not a programmer. If I was a programmer, I would be way more expensive to my university. I'll tell you that. But the thing is, what I want them is to be efficient in what the science and the research does. So what we did is, as you progress through your skills, document everything. And we're going to create a Google Classroom with resources, references, small exercises, small project, but not for the general concept of programming, but specifically with major branches for what we call heliophysics. So that's anything related to the sun effect on Earth. Astronomy, if you're in astronomy, that's more like big data analysis, large amount of data, how you sort them, process them. Robotics, because some of the elements, like what we do, programming a motor to go down and up, that is also part of research. So a really very centered on the element of what is programming for research. You may have the acronym because honestly, it's like Pythagora is Python. What is the T? Oh, I have to find it, but I found the acronym after I wrote it. But I know it's an open course for heliophysics, astronomy, and geophysics with for teachers and researchers with applications. Essentially, that's Pythagora. The letters itself, a bit of shame, embarrassed to say. I was super happy when I found it, but I don't remember what letter exactly
That
it is for. But the idea is to teach a language with the sole purpose of being useful for people in the field of science. There is a lot of theory, but there is a lot of courses out there. But my interest is not in a general application. It's really on trying to say, hey, these are the steps you need to be able to do research. And I want anyone who has an interest to be able to do that. And the best way for me was to start with somebody who had no knowledge of Python, no knowledge of this kind of programming language, because that was somebody brand new telling me, okay, I needed to do that. I needed to learn about that. I need to learn about that before I could actually do something. And that student is the one that completely, from knowing nothing to having a full graphic user interface for the entire experimental setup we have downstairs. And through that process, we are documenting and improving by providing with other students. Hey, try that, go through that. What are you missing? What do you want us to add? And then put it not on a book that to sell on Amazon, but instead of a platform that is completely open. Just a bit like the MIT has open courseware. It's a kind of spirit, not the same thing. Because the biggest challenge I see is the disconnection between learning programming and applying it. And I find that a very challenging course for the students because they are usually fascinated, they're usually facing the need to learn the language as well as the algorithmic. When you do what's called low-level language. I mean, it may um, bring some memories to some of the viewers, in that if you learn C++, Fortran, you have to learn all the language, memory management. And that's on the top of learning the logic of, okay, a for, an if, etc. And that's a lot to do. And I think if you teach algorithmic, you have better tools than this low-level language like MATLAB, Python, Shell, all these programming that are a lot higher, that don't require as much of memory management, are better suited for that and allow us to get students from not knowing to applying their knowledge to a scientific project. That's a spirit of this Pythagora idea.
That's awesome. So now, of course, the topic of this podcast is related to the fact that you received some funding. So what is the money go? If you've already spent some, or what you plan on spending, what is it going towards? Is it labor for the students? Is it for some of those experimental devices? Those kinds of things.
Yeah. So the bulk of it is to support student. Really, most of the requests I do is to support student, both graduate and undergraduate student. This will support a graduate student for 3 years, covering their tuitions and stipends, so to allow them to go to grad school without coming with a hefty debt. So that's really the thing. But also typically paying undergraduate students, because I think there are two elements to it. The first one is, if you work for me, I want it to show. I want to give you something that needs to show. That will be, if I can pay you, it's ideal. If not, will try to make it like an individual study so that you can have course credit. Or I'm going to try to send you to a conference. So that's something also these kind of funds are used for, taking you to a conference so that you can see what science looks like when scientists are gathering, and of course purchasing equipment, so a power supply, valves, any equipment that we need in the lab. So really that's the equipment, funds, travel, equipment, fund, stipend, tuitions, travels are really the big element of where the money is going.
Thank you. So there's one last thing that I typically like to ask everybody because it's out of my own personal interest. How did you get started in science? If you could go back maybe to high school or earlier, somewhere in that area, how did you get this love for science?
Couple of things. I think there is honestly a lot of opportunity that I had when so if I start, I had a logical mind, always had, and I remember an interesting episode when I was quite young. I was probably 13, 14. I mean, don't want to do false modesty, but I was a very good student, because very rare that you get a PhD if you were not a good student to begin with. Let's be honest. And I was in probably 13, 14, and I get like a top mark in the class in literature. And I remember my teacher telling me, "Well, you have a very scientific mind." It's kind of weird to be told by a literature teacher, when you get the best mark in the class in literature, that you have a logical mind. But which is true. I mean, I never doubt that. I mean, I can tell you that when I wrote an essay, I was marking the side of my page with number of lines for each section before I wrote the sections. I knew how long they wanted the things to be. I would mark them. So I knew that's how my mind worked. So that was really a first cue, like, hey, this is My mind is logical. I process things rationally. I decompose problems into from big to small. And another element is I went to France. I did my study, my undergrad and master's in France. I got the opportunity. I wanted to get an experience abroad to do my master's in France and at Penn State at the same time. But like most people in the US, when I moved to the US, college, I realized that college is freaking expensive. Pardon my French there, but it is very expensive. So I spent my first semester at Penn State as a master's student scooping ice cream at Penn State Creamery and working very hard in my classes, showing up in office hours with the person that became my PhD advisor, Dr. Victor Pasco, because I wanted to get some funding to be able to pay and not end up with like a $50,000 bill in 2 years. And when I was able to get that, I did my master's, I did my research, and my master's advisor told me, well, do you want to do a PhD? I asked, well, depends. You have funding for me? I say, sure. It's like, then yes, absolutely. And so I was able to, I chose that path after that. With that, that's what I call the opportunity. Because if I didn't have, first, the support of my family to help me get to the US in the first place, then having the opportunity of talking to a person that was willing to basically take a chance with my work, with my abilities, I would not have continued to a PhD and I would not gotten where I am. So the scientific mind is something I had all the time, and then the opportunities of having somebody that would back me up for my PhD and afterward.
Well, thank you very much. This was a great episode, and I'm appreciative of you joining me.
Mm-hmm. So one thing you can tell the NSF that this time I didn't spend money on Legos because I kid you not. I mean, if you look at my office, you'll see a lot of Legos. Some of them are not here, but I have like a Mars rover over here, a solar system. And what I'm saying that jokingly, but as part of the outreach I did before, the programming idea for people is also something that is existing right now. I run a summer camp where I use Legos to teach middle schooler the basic of algorithmic, how to think like a programmer. And so, but this time the project is not supporting that directly.
Well, thank you very much.
Sure thing.